Ladies and gentlemen, welcome back to another live stream. So in this live stream, I'm going to continue the C programming series. So this is part 4, of course. Please make sure to watch the first, second, and third part. So the first part I covered the fundamentals, and then the second part I made a painting program using Raylib, and I showed you how to install libraries. The third program, we improved on the painting program, and in this part I'm gonna try to teach you the rest of the C programming language. So we still have, like the heap memory, IO, and some other stuff, but yeah. Anyway, let me just share the stream. And hello, Loop Luminary, welcome back to the live stream. How's it going, mate? So I was in a game jam, that's why I didn't stream these days, but here we go, we're back again live. Okay, perfect. Now let me pop out this chat here. And I'm gonna be using, by the way, the C-Line IDE instead of Visual Studio this time, because Visual Studio have really annoyed me. It was very slow these days for whichever reason. I'm not sure what the heck happened with it. But there we go. This is my main IDE that I use. It's called C-Line. It's unfortunately paid. But though you could still use Visual Studio, Visual Studio Code, or any kind of other IDEs. Though I'm gonna also be teaching you a bit of CMake here, as you can see. In fact, even Visual Studio, when you're creating a project, you can actually create, instead of a console project, you can make a CMake project. And then you would be able to write like a script like this. And basically, instead of configuring your libraries and source code and properties of the project in in a GUI settings of Visual Studio, you actually configure it in a script in an entire programming language. Well, it should be called scripting language, but whatever, it's called CMake, right? So here we're just setting the CMake minimum required version. Here we're giving the project a name, and then we're listing the languages that we're going to be using for this project, which is in this case just C. And here we're setting the CMake C standard that we're going to use, basically the C version that we're going to use. And then here in this case I set it to 23, and now here I'm creating an executable target. So like I'm creating a new application, because using CMake I can create multiple applications and multiple libraries and executables, link them together and do all sorts of shenanigans, right? But yeah, either way, here we're adding an executable to the project. Actually, no, that's the name of the executable, right? And then here the source code of the executable, which is in this case only the main.c file here, pretty much. Anyway, let's go further with this. Let me just run. And by the way, I'm actually using, if you see here in the build settings, I think CMake here. Yeah, there we go. Okay, so, apparently I'm using MinGW. So here I could like choose which compiler I want to use. I'm gonna go with Visual Studio, honestly, instead. And let's try this out. And the generator, I'm using Ninja. But yeah, anyways. Okay, and let's see if this actually would work. I just installed this IDE because I reset my system, but let's see. Alright, perfect. Let's try the famous print hello world that we have done in the first episode. So include IO stream, and then printf hello world, just to make sure everything is working fine. Alright, let's see what we got here. An expected compiler, expected the C++ compiler, huh? Not iStream. It should be, what is that actually called? Include stdio, yeah. iStream is for C++, my bad. All right, there we go. Okay, perfect. So what I'm gonna try to do today is to teach you how you can make your own matrix implementation. Kind of like a library, right? That you could use to add matrices together and so on. And I'm gonna also teach you how you can save that matrix into a file and how you can load it. So I can also teach you some file IO. And of course I'm gonna teach you about the memory, the heap memory in the process too. But yeah, anyways, we'll see how it goes. All right, so let's start by making a simple matrix struct here. So type dev struct matrix, right? And so I actually don't know, like I'm not a mathematics guru. So as a programmer, what I can go ahead and do, I can go to Wikipedia, look for a matrix. Well, not this matrix, I mean the mathematical matrix, right? And then I could see what I have here, right? I could see the definition and so on, and then I could program it. Basically. So now the thing is, one thing that I'd like to point out is that if you want matrices, like to just use matrices, don't implement it yourself, please. Only implement it yourself for learning purposes. Otherwise, it's just kind of like a wasted time, right? If you actually really need matrices, you could just look for a library like CGLM, for example. And then you could just use this library instead. In fact, I may make a tutorial later on let's say how you can use such a library, for example, and so on. Yeah, or maybe even today, I'm not sure, but we'll see how it goes either way. But yeah, anyways, let's go back. Right now we're actually going to implement it ourselves for learning purposes, right? Anyways, so a matrix is a rectangular array or table of numbers, symbols, or expressions with elements of entries, arranged of rows and columns, which is used to represent a mathematical object or property such as an object. All right, so an m times n matrix, so like you have two dimensions, m and n, which means that here we're gonna need two dimensions, size t, m, and size t, n. Perfect. And we also have the actual data apparently. So it's going to be float data. And here we could go ahead with an array, for example, with the maximum elements, like 50 here or whatever. But yeah. All right, so we're going to need to create somehow to initialize that matrix. So let's create a function. Let's say matrix create matrix, or you could even say new matrix or whichever, call it whichever you'd like, and then that basically returns a matrix. All right, now let's actually try to construct this, and of course the user would give us two dimensions, size tm and size tn, and then for the data we're gonna see about that later on. And what's happening here? Okay, sure. So let's make a new matrix here. Matrix, or you could call it self, I guess. And then we're gonna return self. Now self.m is equal to m. We gotta initialize the m of the object and the n of the object. You know, because these we're getting them as arguments, and then we have to populate them here in the actual matrix struct. And hello Theo Paris, welcome back to the live stream. And we could add a const here. Okay, cool. Otherwise you could also do it in another way, which is to basically say is equal to matrix, well, like this matrix. This is called I don't actually remember the name. But either way, you do it like that, just like this, and there we go, done. Get either that or that, it doesn't really matter. And yeah, the nice thing though about this kind of syntax is that right now I could make this const if you wanted to, but we still want to do something about that anyways. Or you could in fact just go ahead and straight and do something like this. Could easily, like, straight up go return matrix.m.n equal to n. There you go. Now we need to actually initialize the data. For if we leave it like this, it would, like, all the 50 entries would just basically be you know, zeros essentially. And now the problem with this kind of setting of actually using a fixed array, because we can't really say m times n, because m and n would only be known at runtime when the application is running, right? But this, like the actual length of the array, should be known at compile time. Why at compile time? Because basically this space would be reserved in the actual program memory, right? So it would be loaded with the program in some sense. If you learn about assembly, you would learn more about why this is the case. Either way, this is basically it. Let's actually create matrix. A is equal to a new matrix, and then we give m and n, and that's basically it. Now let's create a way to actually display this matrix into the console. So we're gonna print it basically. So we're gonna have a void print exactly. The AI have got it correct, but let me actually disable it really. Print matrix. All right, so here we're gonna go with matrix pointer, or we could call it self. It doesn't matter the names, by the way. Just do whichever you like really. Anyways, so we got a matrix. We have to basically print this matrix somehow. How are we gonna do that? Well, we're gonna make a for loop going through all the, should I say the rows? Yeah, the rows of the matrix. All right, so how are we gonna do that? Well, size t, m is equal to 0, m is less than self dot m, and then m++, right? So here basically this code would run for every matrix, for every row. This code would run for every row. Now we gotta think about what we want to do for every row to actually print the whole matrix. Well, for every row, right, for every single row of these, we want to actually go through all the columns in that row and print those elements or those values in that row. So that means we need another loop right here. So we need a nested loop. It's called a nested loop because it's inside of another loop basically. Double nesting here because we have two loops, like one inside of the other. Anyways, size t n is equal to 0 and n is less than self n plus plus. Alrighty. Perfect. So that means here we're actually gonna traverse, like, so basically here we would go through every row, through like run for every row m, right? And this would run for every value or column, should I say, in row m, for every column n in row m, right? But yeah, hopefully that makes sense. All right, so what we want to do for every value in the matrix, well, we basically want to print it, of course. So print f, comma, well, now here we need to actually access the data, right? So now the problem here, well, in fact, since we have like a fixed array, we can actually do like something like this. Like we could add another 50 here, and this would basically be a 2D array, right? A two-dimensional array, just like a matrix basically. Though of course the maximum would be 50 by 50 here. But we'll mention that later on when it comes to heap memory. But for now, don't worry about that. So here what we could do basically is self data m and n. Basically, parameter self can be made pointer to const. Okay, sure, add const, and there we go. Perfect. Now we could use our function print matrix, or in fact, if you have an IDE like me, you could say a dot, and then it would show you all the functions that starts with that matrix as the first parameter. So we could say print matrix, and then it would automatically do that for you, essentially, which is pretty cool. Anyways, what's going on here? We could actually add a const here. Perfect. And yeah, that's basically it. Now, one little thing. I mean, let me see what's gonna happen here first of all. And there we go. So this is what we got. Now, of course, this is, we need some space first of all between the values. So let's add a little trailing space right there. And there you go. Now we have some space between these values, but we don't actually jump to a new line in every row. So how we could do that? Well, outside of this inner loop and inside of the outer loop, which runs for every row, at the end of it, after this inner like loop or this, what we need to do is to actually printf new line, right? And let's go. And now we actually have this. We're printing the matrix, so it's 3 by 3. We could go ahead 4 by 3 or 4 by 2 or whichever, and it would actually work just fine. There you go, 4 by 2. Now is that correct? Yeah, so 4 in the M and N2. Okay, cool, lovely. Alright, so that's basically it. Let's say, for example, we want another method on array, or sorry, matrices, that basically check if the matrix is a square matrix, because a square matrix is just a matrix that have its m dimensions equals to its n dimension, right? So square, there we go, square matrices with the same number of rows and columns play a major role in matrix theory. Square matrices of a given dimension form a non-commutative ring, blah blah, whatever. Anyway, let's go ahead and do this. It should be very simple. We could go with bool, though the problem is there is no bool in C. No boolean in C, so we're just gonna go with integer. And we're gonna call this, well, by the way, one little thing is that we usually don't do it like this, like new matrix, print matrix. By convention, we do, like, we actually mention the name of the object first of all, and then the actual action or verb. So here would be matrix new and matrix print, just by convention, though it's your program, you're free to name your stuff whichever you want, basically. So yeah. And alright. Alright, so integer matrix, so this one would be called matrix is square, right? And then of course again it would take const matrix self, and here we're taking a constant matrix pointer because we're not going to be modifying that basically. So here it's actually very simple. Return self m is equal to self n. As simple as that. Perfect. And now let me actually fix this. Matrix print matrix new. Okay, cool. Now the problem with this kind of method using like an array like this is the fact that you can only go as far as 50 members, you know, sorry, 50 elements in both dimensions, right? Which is not great. We want to be able to account for any elements. And by the way, in fact, this would be stored in the stack, and the stack size is very limited, right? So it's not like you have the whole RAM memory for yourself or your program. That's called the heap memory. The stack memory is very limited, just in like a few megabytes, and sometimes even just a few kilobytes, really. Depends on the platform and on your settings. But yeah, so how we could actually do that? Well, instead of using you know, instead of using a double array or 2D array like this, we have to use instead a pointer, just like this. And then here, we're going to allocate some memory. We're going to ask the operating system to give us some memory from the RAM, right? So as I said before in the previous stream, you know, the memory that it would get allocated comes from your RAM, right? So this is how much RAM I have. In my case, I have 16 GB of memory. So basically, I'm going to ask the OS here for some memory. So I'm going to use something called a malloc, right? It's a function in the standard library called malloc, and of course to use that you need stdlib.h. If I say alt enter in my IDE here, it would actually import it for me, and there we go. So malloc, and as I mentioned before again in the previous stream, is that every function you use, you should check out its documentation. So you don't actually have to memorize this stuff. Just look up the documentation basically. And there we go. So malloc allocates size bytes of initialized storage. So it basically gives us back a void pointer, and I haven't explained what a void pointer is yet, but I'm going to do it in a second. And it takes a size t size, and of course the size is in bytes of initialized storage, meaning that the values that would be allocated could be anything really. It could be just garbage values, it could be zeros, we don't know. If allocation succeeds, it returns a pointer that is suitably aligned for any object type of fundamental alignment. Alignment is another concept that you may want to learn later on, but anyways, if size is 0, the behavior of malloc is implementation defined. For example, null pointer may be returned. Alternatively, a non-null pointer may be returned. Yeah, you could read that through this, but right now what's most important is how you allocate some memory. Okay, let's see. So malloc, basically we need to allocate enough memory to hold m times n float values, right? So what we're gonna do then, we're gonna say malloc m times n times size of, because this is in bytes, right? So that means we actually have to multiply by the size of float in bytes, right? Times size of bytes. Oh, sorry, size of float. And there you go. Now we're going to allocate enough memory or enough bytes to hold all those values there. And basically malloc would give us a pointer, the address to where that memory is located, to that allocated memory essentially. Of course, this could fail. So you may want to check like if that have failed or not. Like you could basically say here, float data is equal to malloc. So like you could grab this here, put it here, and now check if data is actually null or not. So if data is equal to null null in C like this. So if it's equals to null, that means we're cooked, right? We couldn't allocate memory for whichever reason. Maybe the operating system doesn't have enough memory to allocate that size that you gave it, or whatever. We don't know, right? Allocated memory is leaked. Well, memory leaks. Okay, well, I'll have to teach you about that. Anyways, if data is equal to null, it means that we have failed the allocation. And so here we need a way to actually tell the user of our library. Let's say we're creating this library for users, you know, to use. We gotta signal somehow to the user that there is a problem here. Now, one rough way that we could deal with this is to just exit the program violently and call it a day, really. And that's what I'm gonna do for now. But later on we're gonna see some better ways to do this. Anyways, if data is equal to null, then exit 1, otherwise we're gonna use this here. Is implicitly convert. Well, let's remove that const there, please. Thank you. Now, allocated memory is leaked. Why? Because, well, whenever you allocate memory, you have to free it somehow, because in C, like, you actually allocate your own garbage. You allocate, like, you manage your own memory, right? So anything that you allocate, you have to free yourself. So we need another function, let's say, called, it's not like the stack memory, like the arrays and so on, which basically, and the variables that you allocate in the stack, like once you exit the scope, they're no longer valid, right? That's not the case here. In fact, like you, well, let me not go into those details right now, actually. Yeah, let's not go into those details right now. Anyways, so void matrix destroy, or free, let's call it free, fine. So matrix free, and you give it some matrix, right? And now we need to free the resource that this matrix allocates. In this case, we only have one thing that we get a free, which is the data that is pointing to by this data, right? So we gotta say free self data, too simply. Parameter self can be made pointer to sure. Why not? And by the way, this basically returns, this malloc right here actually returns a void pointer, not a float pointer. And void pointer basically means a pointer that points to really anything. It could be anything. We don't know what kind of type exactly. And so basically, you have to actually, like, if you want to use that pointer, you have to cast it to some other pointer type. In this case, we're casting it to float because we already know that this pointer needs to, like, is actually, or at least should be pointing to a float array kind of thing. Anyways, so now let's see what we gotta do here. Now the problem right now is that we no longer have like a double, or like a 2D array here. What we actually have is just one-dimensional array allocated on the heap. So how we can actually access that? Well, we could say float matrix get. And here I can make use of AI real quick. Let's see if it's gonna figure it out. There we go. Let's go. So you just say self matrix. You give it the M and the N, like which index you want to access, and then we're returning an address to the data pointer, like, and then we use M times self N plus N. This is basically the formula to access, like, in a 2D fashion, but in a one-dimensional linear array. I may try to actually explain this better in some sense here. I don't know. Let's see. So let's say we have a matrix, right? A and B, C and D, right? So how we're actually storing this right now is by actually just having an array like this. A, B, C, and D. Well, just like that. And then we're doing this kind of formula to actually convert that M and N coordinates in two-dimensional space into one-dimensional index, right? So we got like a two-dimensional index, M and N, and then it goes through that formula and it become one index that we could use in this to index this linear array, basically. But yeah, let's see if this works first of all. So if we go here, say matrix get, and then here we need to pass in the self, comma M, comma N. Now the problem here is that it actually gives us a pointer to a float. And why I said a pointer? Because we also want to be able to actually edit that value. Though for the sake of this function for now, we could just say a float and then we don't need this address here. And so it would just give us a copy of that value, really. And yeah, let's actually try this first of all, really. Let's try this. And oh, as you can see, it have just some garbage values because we're not initializing this like yet. And by the way, there's also another function called calloc that we could use. It's kind of like malloc, but a bit different. So it allocates a memory for an array of number object sizes and initialize all bytes in the allocated storage to 0. So this one actually allocates everything to 0. It's not an initialized, right? And also it gives us two sizes, like the number or like the count of the array and then the actual size of the object. So we could make use of that. So you could say calloc, basically calloc. So the count is in this case M times N, and the actual size is float, size of float. And yeah, and I kind of hate this allocated memory is leak, but anyways, whatever. matrix free. Right now, since we're using calloc, it should be zeros. There we go. It's all zeros right now. Perfect. Perfect. All right. Now, let's say we want to actually create an identity function that would initialize the matrix to an identity matrix, right? So like if we go back here, is there like an identity matrix here? Let's see. There we go. So an identity matrix is basically a matrix where like the actual diagonal of the matrix is all ones and the other values are zeros essentially. So how we could do that? Well, void matrix identity, and we're just gonna get const matrix self, right? And now we need to again basically do the same kind of loop that we've done here again, because we want to go through the all the values in the matrix. And then what we basically want to do here, we gotta check if m, but I'm gonna deactivate the AI real quick. So if m is equal to n, meaning that we are in the diagonal, then we want it to be 1, equal to 1. Now here, let's get the value, right? So float value is equal to matrix get. Well, it should be first before that, right? So, okay. And honestly, I'd also like to keep this paired with the matrix new here. Okay, cool. So here, matrix get, we need self and m and then n, basically. Perfect. Now, the problem with this is that this is giving me a copy of the value here. It's not giving me a pointer to it. So since it's giving me a copy, I can't, like even if I change this value, it wouldn't really change the original value that is sorted. Like it wouldn't change the actual memory location that this matrix resides in, right? So then how can I actually change the matrix data itself instead of changing its copy? Well, I should basically make this a pointer instead, and gives a pointer, an address to that location in memory, right? And so now I'm gonna say float value pointer. Now if m is equal to n, then we're gonna basically dereference that pointer or that address in memory, and then we're gonna set it to 1. Else, if it's not in the diagonal, meaning that m is not equal to n, then value should be 0, should be equal to 0 essentially. Now this only makes real sense if this matrix is a square matrix. Like identity matrices doesn't make sense in any other context other than a square matrix. So one thing that we could do here is that a precondition for this function to work is the fact that this matrix should be a square matrix. Now if we had a more type safe language like Rust, for example, or even maybe, yeah, C++, then we could actually do this, assert that at compile time, but we don't have that luxury in C. So we have to do it at runtime, meaning that we can't do this like before the actual program runs. It have to run first and hit that point before it gives us that error. But anyways, that doesn't matter. So right now, let's just say assert. So there's a function again in the header assert.h in the basically the standard library, right? It's a function. Well, it's in fact a macro, but well, it's kind of like a function. Anyways, so we're gonna assert that the matrix is a square matrix. So matrix is square. I'm pretty sure I have programmed that. There we go. Let's actually grab that. Now let's come here, and there we go. Okay, so matrix is square, and then we're gonna give the matrix. So we're gonna make sure that it is a square matrix. Now here, and also here, you gotta dereference the value to get the actual float value there. Okay, so we can print it basically, and I think that's basically it. All right, let's see. So matrix print, cool. Let's say matrix identity. Now this should result in getting a search triggered there, because this is not a square matrix, it's 4 by 2. So let's see what's gonna happen. And what the heck is going on here? Syntax error identifier. Oh, I think maybe I have, hold on, let's see. That's strange. What the heck? I have no clue what this error is about. Oh, what the heck? My IDE sucked there, so let's just include it ourselves. Assert.h, there we go. Anyways. And there you go. So as you can see, we got a debug error. And this is where the assertion failed. Matrix is square self, meaning that the matrix is not a square matrix. So that's good. Righty. So basically the program would crash if the matrix is not square. Like to alert the user, like the programmer that is using this library or this object right here, this matrix object, that you can't do this here, right? So let's say, for example, 4 by 4 matrix, and in fact, let me print it after the identity, or I could do it both, like after and before. Why not? And let's see what we got here. And there you go. So let's see, this is beforehand, it's all zeros. And afterwards, we have 1, 1, 1 in the actual diagonal here, which is perfect. There we go. Alright, matrix is square, matrix get. And this is annoying me. Let me make sure to free this matrix. Matrix free, yeah. A. Would that error right now go away? Let's see. It's a warning, but I'm not sure. It's probably wrong. I mean, I'm freeing it here, basically, so it should... either way, let's go back to this kind of thing. What happens when we actually have data is equal to null? Now, we can't really do much here unless if we actually remove this matrix from here, say void instead, and then have like an output parameter instead of returning a matrix value. And the nice thing about this also is that the user is free to put this matrix wherever he wants. He can allocate it on the heap or use the stack, doesn't matter. He can do whichever he wants, instead of us returning a matrix through the stack here. So, but of course we cannot use this kind of syntax anymore. We have to do it like this instead. Matrix m is equal to m, and matrix n is equal to n, matrix data is equal to data. Perfect. Now if data is equal to null, we could just return without actually changing anything in this matrix. But a better way would be here to actually tell the user that something happened wrong here. So if everything goes well, we could return a 0, let's say, to indicate success, right? So integer return 0, or like you could say success exit 6. Nah. Let's just keep as it was. Return 0, and for example here we would return 1 to indicate failure. We could also create an enum here for status code, so like matrix result, basically, and matrix result success, which is going to be equal to 0 because it's the first element there, and then matrix result failure. and this would basically be 0, and this one is 1 basically. So this is just enumeration, and each element that you add here would get the next successive number, or should I say integer, right? And here, instead of just saying 1 and 0, we could actually make use of these named values, or should I say kind of like constants basically here. So it's pretty much the same, it's just that it's much more clear what you want to do here. So matrix result success and matrix result failure, because we couldn't allocate memory here. And so yeah, data is equal to null. Then, and other than that, you could also say, instead of if data equal to null, you could say if not data, but meh, just keep it explicit like this. If data is equal to null, return matrix result failure. And yeah, and then afterwards here you could actually check for that stuff. Now I can't do it like this anymore. I have to create a matrix on the heap or on the stack. Let's go with the stack for now. Let's call this A. Now I have to basically pass a pointer to it here. Well, actually here, A, and there we go. That's how it goes. Now, if I actually want to allocate this on the heap instead, what I could also do is I could say A is equal to malloc size of matrix, right? And then I could just pass in A directly here. So this would then make sure to allocate the entire matrix on the heap. Though this is not really needed, because like the actual data itself is already on the heap, so why bother, right? But anyways, matrix new 4 a matrix print matrix 3, and here you could check if it's failed or not. So if matrix new is equal to, you know, failure, matrix results failure, then we're just gonna return exit failure. This is like a constant in a header file, and it's I think it's stdlib.h, right? And this is basically just one, right? Just a macro, and here we could say return exit success basically. So yeah, pretty much. So if we couldn't allocate or create the matrix, then we're gonna return with an exit failure error code essentially here. But yeah, now let's do something more interesting, I guess. Let's say we actually want to save this matrix into a file. Now we can do that. Or honestly, let's do something more basic, like adding two matrices together and multiplying them, etc. Well, multiplying them is a bit harder to do, but yeah, let's go with adding two matrices together. Let's see how we're gonna do that. Well, you're gonna have void matrix add, and here we, oops, what I'm doing. Okay, so here we're gonna get two matrices, const matrix self and const matrix RHS, or right hand side, or you could call it other. You know, now the thing is, we have like a design choice to make here. We can either like create a new matrix altogether for the result, or we could just like add the result to self. Now this is an add function, right? So I would actually return a new matrix, honestly, right? So yeah, so how are we gonna do this? Let's see. So you're gonna create a new matrix, right? So matrix new, or should I say result, is equal to, so I'm gonna create, like, use my function that I've made before, which is matrix new, right? And so the m would be the same as self m and the same as self n, and well, the new matrix would go to result, right? So let me remove that from here. Let's go here, yeah. And honestly, instead of doing it this way, I would again say integer. Or in fact, instead of integer, I could also use this kind of enum as a return type, like matrix result, I think. Yeah, but I have to make sure to do it like this. First of all, type def enum matrix result like this. Basically, and there we go. So here, where is that thing? Matrix add, matrix new. Now I should make sure that they match, like the self and other match in the dimensions. So we could have like another function, integer matrix, you know, match dimensions, I guess. Match, or like equal dimensions, is equal dimensions, let's say. And then you would basically have two matrices here, and it would basically return self m is equal to other m, and self m, well, self n equal to other n. And then here we could assert that the matrix is equal dimensions, and like self and other here, and there you go. So that's our precondition right there. Perfect. Now here we got our result matrix on the stack, and then we initialize that matrix using our matrix new function here, as you can see. And now we have to actually add those matrices together, and so we're basically just going to do the same exact thing that we kind of did here, right? So I'm just going to copy that over, paste it here, and what we're going to do now is we don't want this stuff here. So we're gonna get like the elements from both matrices. So like we're gonna have float A is equal to matrix, well, pointer there. Or honestly, it doesn't really have to be a pointer. Yeah, we could just dereference it. We just want to get the value there. Float B, same thing here, but instead of self, we're gonna go with the other matrix, right? And now we're gonna say result. Well, float C is also equal to matrix get. Now here we're gonna go with the result, comma m, comma n. Now, here we do need a pointer because we want to change the result, right? So here we could say C, we're gonna dereference it, and it would be equal to A plus B. Cannot convert matrix parameter. Yeah, let's actually give it that, and there we go. All right, what's going on here? Alt Shift Enter. Oops, what the heck? Strange. Anyways, add const. Add const. And that should do the trick, I think. No return statement. And finally, when we're all done, I'm gonna say return result, basically. Well, not that. We actually should say, well, we need the output parameter. So it's gonna be like matrix result. And just by convention, usually the output parameters like that are used for output through a pointer, they are at the end of the argument list. But just by convention, you can do whichever the heck you want in your own program. But yeah, alright, so result is equal to, no, what I'm doing. Actually, we could just do it like this, yeah. There we go. And now, that's really it, yeah. So we're just gonna get a pointer to a results matrix from the user. And to be honest with you, we could even let the user himself. No, it's fine like that, I guess. Yeah. Alright, so how I could actually use this now. So I'm gonna ignore errors honestly for now to keep this simple, but I gotta show you something about memory leaks though. So let's keep them, fine. Matrix B. So we're having a second matrix there, and we need to of course initialize that to here. So matrix B. Yeah, and now here's one little thing, which is the fact that if this fails and you return from this, then you have basically leaked the memory of this matrix right here, because it's already allocated, right? But you have to make sure to deallocate. Now here it doesn't really make sense since you're like, I mean, it doesn't matter since you're exiting the program anyways. But if this was in somewhere else where the program wouldn't exit, like, and it would keep on going, this would be a memory leak, and like the memory would keep on piling up for your program until you don't have any memory left, essentially. You could like let's say for example this happens every frame or whichever. To make sure you don't have any memory leaks here, what you would say is if the second matrix failed to allocate, then you have to free the first matrix before you exit. So like you gotta say matrix free A here. There we go. And finally, you got to make sure to free the other one here too, and the end of it. And there we go. So yeah, matrix new. Now here we also gotta check. So if matrix new result. Like if it's equal to fail, or if it's not equal to like matrix result success, then we're gonna return that status code. We could call it status code or code or whatever. Then we'd say, well, matrix result. Actually, let's call it, well, not result. Let's call it code, fine. And so if it's not equal to success, then we're gonna return out of this function with that code, basically. Yeah, add const. There we go. Oh, here I'm not returning anything apparently, so let's actually return matrix success. Basically, and there we go. So if it's not success here, then we're gonna return from this function before doing this stuff right here. And yeah. Now let's actually try to make a third matrix, matrix C, where it's gonna be basically A plus B. And so for that, what we're gonna, so here we're actually initializing those two matrices. And then matrix free, and we should also make sure to free the third matrix, matrix C, that we're gonna allocate in a second here. So honestly, I'm gonna keep matrix identity for A, and I'm also gonna make the B matrix as an identity matrix too. And then the C matrix would basically be the addition of those two identity matrices. So matrix add. Here we get self and other, which is A and B. And though we probably want to give an address there, yeah. And then finally address to C here, which is going to be the actual result. Alrighty. Now we have to actually check to make sure that that was successful again. So of course, if you want to check, like, you could actually skip all these error handling parts, and honestly I'm gonna skip them. I just wanted to show you how to free memory without having memory leaks in a real program. But yeah, matrix result failure, matrix add. So here, if that happens, if that fails, then we're gonna free A and we're gonna free B too, because both were successfully allocated. And then finally we're gonna return exit failure. There we go. So yeah, this is how you handle, you know, errors without having a memory leak in C manually. Now, if we had C++ RAII, or let's say Rust drop trait, we wouldn't have to do this manually. Once it goes out of scope, it would go out of scope. It would get destroyed automatically, kinda. So yeah, but in C we have to do it manually like this. Hopefully that makes sense. But you could see, so for the sake of simplicity, I'm not gonna check for errors anymore. And in fact, it doesn't matter in this case, since we're exiting the program anyway, so we're just wasting time of freeing stuff up really here. So yeah, so I'm just gonna ignore the errors. And it's very unlikely that it would actually fail to allocate memory in this case, so yeah. So this is way easier to read right now. So we're creating two matrices, A and B, of course in the same dimensions, 4 by 4. And then we're making the first matrix as an identity matrix, the second as an identity matrix, and then we're adding them together into C. Now let's actually print that matrix. So c.print, well, matrix print, and let's see what we get. Pretty much. And there you go, we actually have added them together, because, well, you add two identity matrices, you get this. So 2 in the diagonal, right? Because 1 plus 1, of course, 2. All right, lovely, cool. Now, one little problem, by the way, with this kind of matrix add design is that it allocates memory itself, right? So if you don't check out, like, let's say the documentation of this matrix add and the actual library, like who implemented this matrix library told you that it actually allocates the results matrix, or you check the code yourself to see that it actually allocates memory through this matrix new function, then you would have a memory leak easily, right? So a good design choice would be to never allocate memory, like to let the user always allocate memory for you, right? And so what we're gonna do to fix this design choice is to actually, and we also don't have to like handle this allocation result anymore. So it would be just a void function here, and we wouldn't have to deal with this stuff anymore. Though right now I should also assert that matrix is equal dimensions, you know, self with result, right? And since of course that self is like have the same dimensions as other, and self have the same dimensions as result, then of course result would have the same dimensions as other. Well, it's transitive, you know. Anyways, what the heck, hold on. Yeah, const matrix result, cool. And we don't need result anymore, and there we go, perfect. And now what we gotta actually do here is to also allocate the third matrix, C, ourselves, and then add would to simply just add these matrices together and add them into the results. The other nice thing about this design of the add function to not allocate ourselves inside this function is the fact that like the user could actually just override an existing matrix and reuse it in this matrix add function because it doesn't allocate. So that's great. All right, perfect. Now this would still work the same way, it's just a better design. There we go. Cool. Lovely. All right, so I think that's it for the add function. All right, so let's say we actually want to save this matrix into a file. How we could do that? Well, first of all, where's the matrix print function? We could actually make this. Now, there's two ways we could do this. We could either make an entirely new function, or we could just reuse an existing function and add more parameters to it. Now, in my case, I'd rather just reuse this function right here. And if you check out the documentation of the standard library, there's another function called fprintf. And this function takes a stream first, a file, and the printf basically calls fprintf with the file stdout for standard output, basically, which is basically the console, right? And so instead of that, like, this is basically the same thing that you had before with printf, as you can see here. But now what we could actually also do is to basically grab the file stream here. So there we go, stream. And instead of stdout hard coding it to stdout, we could get it as a parameter in this function, and there we go. We could use that stream if thing right there, which is cool. And we don't need those brackets there, but yeah. All right, so now what? In matrix print here right now, to have the same as we had before, we have to say stdout. And there you go. This is the exact same thing, right, that we had before, the same functionality, but our matrix print function is more flexible right now because it can print to anything, it can output to anything, really. It can output stdout or any other file. Now we gotta figure out how to actually create a file. Now let's say I don't know how to create a file. How can I figure that out? Well, I'm just gonna go to any search engine, say how to create a file in C. Right, and then you're gonna go to and see what you're gonna find there, basically. Right, so as you can see, you create a pointer for a file, and then you use this function fopen to open a file. Now, if you actually read through this, you're gonna understand, or I already know how this works, so I don't have to. Though even myself, I still have to check out. I don't really always memorize this stuff, right? So it could just come in back and check out how it's done. The only difference between me and you is that I already know how those work. I just don't remember exactly what to type in, so I have to use this as a reference, kind of. But for you, you have to reread this whole thing and make sure you understand what's going on here. Anyways, let's see how this is done. So let's create a new file here before the printing. So file is equal to fopen, right? Yeah, is equal to fopen file name. So here the file name is the path to that file, like the actual name of the file, right? So let's call this, I guess, matrix.txt maybe. And then the mode of writing. Now you could check out this stuff here. So if it's a W, then it would write to a file. If it's A, append the new data to a file. And if it's R, then reads from a file. So here we want to write to that file, so we're going to go with W there. Perfect. Now if you check more details about the fopen function, you're going to find, well, what the heck? We're going to find out what it actually returns. well, let's see, return value. So it returns a file pointer if the file is successfully opened. If the file cannot be opened, it returns null, as you can see here. So you gotta make sure it is actually opened correctly. So if file is equal to null, that means we have a problem. So like we could exit, or like we could return exit failure and tell the user that there is a problem, like printf couldn't open the file matrix.txt for writing. Now you can actually get more details about why that failed, but let's not go about that for now. And also another thing to mention about error messages is that it would be better if you say fprintf, and instead of using stdout, which is the default, you would use stderror, standard error, which is going to be read in some terminals. So that's great. And also it does serve another purpose in more complex terminals, but let's not go into details right now. And function is open is deprecated. Consider using fopen_s instead to disable implication, blah blah, whatever. Alright, so now we open the file. What we could do is to basically, instead of using stdout, we're going to use the file itself. Let's remove this const here, and yeah, let's actually try this. Now, instead of printing that matrix into stdout, it should have made a file here, but it haven't apparently, which is interesting. Did it run correctly, Dynaway? Well, let me make sure. One thing is to actually close that file, and it's quite important to close it. And let's try again. Let's see. And it actually finished with exit code 0, meaning it was a success, apparently. Okay, where's the actual file here? Interestingly. There we go. Interesting. So, and this is what we got in the file. Oh yeah, I forgot one little thing, by the way, which is that I haven't changed it here. So fprintf stream here too. And yeah, let's go now. Yeah, it should be here. There we go. And as you can see right now, we have it like written into a file instead. Perfect. Instead of matrix print, maybe we could even make this more clear and call it an output, but anyways. And let's see. And we could have like another function called matrix scan. And this would basically like input a matrix from some certain string. So basically const matrix self file const string. It's gonna be the exact kind of same thing here, but instead of using fprintf, we wanna actually like use scanf here instead. Huh, really? So we have few choices that we could do here. Honestly, let me not go into that for now. We can leave it for later on, really. So that's gonna be a bit more complex. Anyways, so this is basically how you create a new file. Then instead of saying stdout, you say file. If you want to print it to both the file and stdout, then well, you just do it twice. You say stdout here too simply. There we go. Right, now this function is apparently deprecated. Now there is one way, which is to just define this macro and it would disable those warnings for you. Oops. Define this macro and this would no longer error anymore. Or you could actually really fix that error by using that thing that I talked about. Which is that it told us to use fopens instead. Let's check out what that fopens instead is. Okay. So it takes a pointer to the file pointer that receives the pointer to oh my god. That's a very bad description to a new programmer. But it's actually not that hard. I'll show you how it works. So the name of the file to open, tab of access permitted. Okay, cool. Cool. So basically it's a double pointer here, right? It's not just one single pointer, it's a double pointer. So how this works basically is fopens. So we're gonna say file, so we're gonna give the address to that pointer. Why we want to give the address to that pointer, like a double pointer here? Because basically the function fopens, it doesn't want to give us a file itself. It actually wants to give us a pointer to a file. So we need a second pointer, a second indirection. So that's basically the case. So basically it wants to change not what the file points to, but the actual point at the file address itself. Hopefully that makes a bit of sense. But anyways, file name here, so matrix.txt, the mode for writing here, oopsie, well, there we go. Fopens, and now what this returns, 0 if successful, and error code on failure. For more information about these error codes, see error now. Alrighty, an error code on failure. So basically if that's not equal to 0, then there is a problem. Now to actually get more information about that problem, there's something called error now, as you can see here. Now we could read through this, but there is another function for error now that is quite useful, which is called perr here. It would print an error message, like a user-friendly, or should I say human-friendly error message to the user basically. So prints an error message to std error, as you can see, the standard error stream is a wide character version, blah blah. Alright, so how I could use that, we just give it some message here to print. Alright, so what we could basically do here is I could return exit failure code, too simply, and before that we could print an error message to the user, matrix.txt to be opened for writing. And then actually perr would give the user more information about why that's the case. But yeah, like for example, it could be that it doesn't have permission to actually, let's say, open that file or something. But anyways, or maybe something else is reading that file. But yeah, whichever. Alright, so that's basically it. Basically it. Alrighty, what should I implement next? Let's see. So as you can see, I kind of covered here files to some degree. Not everything though about files. A bit about heap memory, a bit about error handling, and yeah. The other thing that we could potentially do here is use a flexible array member. Well, actually, no, it's not needed here. Yeah, one other aspect that I should actually talk about here. Let's say we actually want to copy a matrix. So here, if you notice that A and B are actually this, like they have the same contents, but they're two different matrices here, right? So in fact, I could indeed remove the matrix B here entirely and just add the matrix A with itself, really. And this, of course, would be multiplication by 2. But you get the point. It's the same exact thing here. Now, let's say I actually, instead of allocating the new matrix and then like initializing the same way I initialize the other matrix, let's say I just want to directly copy that matrix. How can I do it? Well, one way you may think about is to simply say matrix B is equal to A, right? But that wouldn't work for quite a lot of reasons here. So basically what's going to happen here is that we're going to copy these things, right? We're not going to copy the allocation. We're not going to create a new allocation in memory for the new data or for the new matrix. We're going to reuse the same pointer, the same address, like we're going to reuse the same memory, right? Which suck. Why? Because if you change A, then it would also change B because they share the same memory. So you're not really copying the matrix. You're actually aliasing the same, you're referencing the same matrix here. And in fact here it's even worse because here it would be copied over, but then you would change A here, but this wouldn't get updated. But anyways, whichever, how we can actually copy the whole matrix. So if we change one matrix, it does, like the other doesn't get changed. That's basically the real question here. How we could do that? Well, let's keep matrix B as it was before, but now, I mean, we're still gonna say matrix new for well, C here. Okay, and then here B. Alright, so matrix identity A. So after initializing A with identity matrix, we want to copy that. So matrix copy B A. So basically, we're going to copy from A to B. So how we could do this? Let's implement that. So void matrix copy. Const matrix self, I think, and then const matrix other. Now I'm gonna have something similar to this. And I have like a nested loop right here. Let's remove this part. And let's see what we're gonna do here. So let's say this is A and this is B. Now, which is the source and which is the destination? Destination would be self. Yeah, we're gonna mutate self, which is A here. So you're gonna say A is equal to B, basically. Or else you could just directly do this. Yeah. So we're dereferencing B to get the actual value. Then here we're dereferencing A to set it to B. There we go. That should work. Let's see. And whoops, I got a problem here for some reason. Access violation. Radial location 0xFFFF. Interesting, huh? Oh, apparently if you see here self, M and N are huge values, which is probably means that self is somehow not initialized or something. Which is B. Yeah, it is not initialized, as you can see here. So let's do that. Let's go. And there you go. So right now we have the same result. Right now, instead of constructing a new like matrix, we're just copying over the values from another matrix, as you can see here. Perfect. All right. Now we could also create an even more advanced function. Let's say matrix, well, component-wise operation. So we would basically get const matrix self, const matrix other, and then the result. Yeah, all right, let's grab all these. And basically we're gonna have this again, or isn't it? Yeah, pretty much. And then now here I want to do some custom logic by the user, right? So in some way I need to pass in a function through this function. Well, let's see how we could actually do that. So this is called something like function pointers, basically. So C function pointers. And I also don't remember the syntax of this. Function pointer in C. And there we go. There we go, there we go. But there was like a way to actually define it as a type. I don't even remember that. There we go. All right. So you do it like this, I think. Function pointer. No, I think there was like a type def thing. There you go, exactly. There we go. So you'd say type def, and it would call this function pointer or whichever. I think so. Let's call this, I guess, binary operator, and it would take 2 doubles. And the double pointer for the result, I think. Why this doesn't work? Ouch. Whoops, like this, yeah. And basically what we're gonna do is gonna do something like this. And then we're gonna take a function here, f of type binary operator. So this is a little bit of an advanced thing in C, but there we go. So like f, a, b, and then c. And whoops, not double, I mean flow actually. F, A, B, C. Otherwise, we could also, well, by the way, this should be void, really. Otherwise, we could also make this return just a float. And then do something like that instead. FAB. That would also work. So, yeah. Right, let's go with that one. So let's actually right now reuse or this use this matrix component wise function that we created here in matrix add instead of doing it manually. How I could do that? Well, we need an add function. So, and it should have this kind of signature basically. So it should have float. Let's call this add binary operator, for example, or whatever, just call it add really, whatever. And it would basically take two floats, a and b. It would return a float, and here it's going to return a plus b. This could be const. And now what we could basically do, let's first of all define this beforehand. Now, instead of all this stuff right here, we could actually just say matrix component wise, give itself other result, and finally f, which is add in this case. There we go. So now the user of the library could actually pass in any function pointer that have the signature of the binary operator here, which basically means that it takes two float parameters and returns a float. Any function that has such a signature could be passed here, and that would work. Well, at least in theory. Let's see what's going on here. There we go. I'm not sure why it took some time there, but there we go. It works. Add function, matrix add. Now we could do the exact same thing with the other ones. We could just copy this a few times. But let me just go step by step. Let's say subtraction, right? So you'd say sub a minus b, right? And then matrix sub. And then you would just pass in this as a function pointer here. There you go. Now if we say matrix sub, instead of add, it actually subtracts. And you would get a 0 matrix. Come on, I'm not sure it's taking time to... There you go, okay. So you can see how easier right now actually to find new component-wise operators by just doing this. But yeah. Alrighty, is there any questions so far? Any questions so far? So I'm gonna take a little break, 5 minutes break, then come back. Okay, back. Alright, so one thing that I've noticed already, just by convention, as I said, I'd like to keep the results, like the out parameters, as the last ones. So let me just switch the actual order of these here. So matrix component wise here, so F first and the result last. Add const. Yeah. Now honestly, to avoid like defining all these in the library itself, you could just let the user do it themselves, right? So, but whatever. Alright, so, oh yeah, it should be like this instead. Result, matrix add and matrix sub. Alright, let's actually put this into its own header file, because this main function, as you can see, it's getting very huge, right? So how I could do that? Well, let's make a new header file. So see header file, and let's call this matrix.h. And okay, alrighty, perfect. Now instead of describe, just say pragma once, call it a day, right? Okay, cool. And alright, so we're just gonna copy this whole thing to there. And we're gonna include matrix.h here. Though notice instead of using these things right here, I use these things instead, quotes. So instead of these angle brackets, these quotes. Because this file or this header is actually in the same file directory, but this ones are in another place, in a built-in place, but whatever. Alright, cool. So, and we don't need assert.h apparently here. Now, yeah, definition, inline specify, I see. Alright, so basically what's telling me is that any function that you give an implementation for in a header file, you should give it an inline declaration specifier like this. So we could either make these inline or use this as an actual header file, and usually only want the header file to only include the actual declaration, not the implementation. So where you want to include the implementation is you want to create a second file, which is a C file, which you're going to implement those stuff, right? So matrix.c, right? Okay. And here what I'm gonna basically do is I'm actually gonna copy this whole stuff to matrix.c here, and in matrix.c I'm gonna actually include matrix.h, right? And there we go. So I copied all that. Now in matrix.h I'm gonna remove all the definitions and leave only the declarations, basically. There we go, honestly, such a basic function like matrix is square is kind of fine to keep it as inline. It's not too much, but well, whichever. Let's just not bother right now. So yeah, as you can see, the header file only contained the declarations basically, and I need some header files for size t here. Alt enter. So it's inside of std_diff, the size t, and this file is in stdio.h, and I think honestly, yeah, size t is also in stdio.h, so that's all we need for the header file. And now matrix.c, it actually needs stdlib.h. What else? And yeah, we need also the assert function from assert.h. And that's basically it. Now we have the declaration and the actual implementation separate. Though these const specifiers doesn't make like they're necessary here in the declarations basically. But if I actually do this, I can remove them all, the whole file. There we go. Perfect. That's much nicer. Now let's go back to here. Now by default, like automatically, my IDE actually added these matrix files into my executable here, which is kind of fine here. Let me make sure this still works. There we go. It's kind of fine. But like what you would actually ideally do here is you would create a library out of that matrix for the matrix basically. So add library matrix. So you would create your own custom library here. You can call it whichever you want. In my case, I'm calling it matrix. And then afterwards, you would add in the matrix.c file here. Right, and that's basically it. Now, of course, you would, well, there we go. And now we shouldn't add these here. And then what we should do is link these libraries. So link libraries, I gotta include my executable here privately. I'm gonna link to the matrix library. So the name that is here, and the name that is here. But yeah. So now I'm basically creating a new library, right? And then linking it. If you actually check here, you may find a library somewhere around here maybe. Let's build this. And resolve external symbol, huh? Oh, sorry, target link libraries. So as you can see here, if you don't link them correctly, then it basically would tell you in resolved external symbol, because yeah, it does have the header, but it doesn't, you didn't link the thing, right? So entitled private matrix. Now let's run this, and notice that we have here matrix.lib, as you can see, and you could even make this a dynamic library instead if you want to. But yeah, there we go. Perfect. Or you could also make it a header only library, but that's probably too much for this video, or should I say this live stream. We already covered too much, pretty much. So yeah, is there anything else I'd like to cover? Hello, V2 Agustin Idioti. I'm finishing first year for CS faculty. I want to start learning C on the summer. Did you recommend me to start with the old C book? Do I recommend to start with the old C book? You mean the one by I don't remember his name. I think Carnegie C book. Kernels, I'm not sure how to spell it. So this guy, this book, I do remember going through this book, and I mean it's a bestseller, so I can't say that much about it. I mean it's fine, although it's kind of using a very old C though, but yeah, it's fine, not bad. Yeah, not bad. But yeah, honestly, the thing that I would recommend most is to actually practice to write a lot of code, like to just pick out some personal projects and try to implement them in C. So like for example here, to cover the heap memory files and so on, I chose to implement a matrix library in the stream, and yeah, there we go. That's it. Is there any other questions on what we have done today? Matrix identity, copy. Thank you, you're welcome. Let's say we want to have a function called swap, which basically takes two matrices and swap their values, right? So the content of the matrix A would be the content of matrix B, and the reverse is also true. So how can that work? So void matrix, well, first of all, we have to define the declaration of this function in the header file. So basically we gotta define the signature. So void matrix, instead of copy, we have now swap. And of course you're gonna get self and then other matrix, and that's basically it. Now we're basically gonna implement this now in the matrix.c here. So how we could do this? Now let's start by a simplified example of swapping stuff around, which is that let's say you have two integers, a, let's say an integer b, right? Well, let's actually call it something else, like let's say x and y, right? And we basically want to swap these values around. How we could do that? Let's make a function to swap two integers together, right? So void swap. Now if we say integer a and b, that wouldn't really work. Like we would say integer c equal to a to store the initial value of a, then you would change a to equal to b, and then you would set b equal to the old a before you set it to b, right? So you'd set it to, well, let's call this temporary, so you know that it is actually temporary value here. So yeah, oops, see what I've done there. And there you go. But this wouldn't really work because these, like, you would only be changing the copies that you get to the function, right? So to actually change the values themselves, we have to take a pointers, right? So we can change the actual memory behind those variables. So alrighty, so the temporary value would, well, basically dereference a to get a copy. Then we will dereference a to set it to b. Of course we dereference there too. And then finally we dereference b and set it to temporary there. And that's how we do it. Now if we say swap, of course x or y, then these values should be swapped around. Let me show you how it all works out. In fact, so I'm going to use my debugger here and put in the breakpoint, and let's see what happens. So first of all, we define x equal to 10, then y equal to 20. And then let's go inside of that swap function. And there we go. So now we got the address of both the a variable, well, in x in this case, and y variable, so like a and b. So as you can see that a right now is equal to 10 and b is equal to 20, and this is the address in memory. And in fact, I could probably jump to show in memory view. There we go. So this is the actual values in memory, in fact, even, and this is the address in memory. But whatever, that doesn't matter here. So now let's see what's going to happen. So first of all, we have a temporary value, which is going to be equal to 10 because we set it to the value of a, right? And now here we're going to set a equal to b. So notice a would become equal to b. There we go. So now a is 20. And now afterwards, we're going to set b to equal to temporary value, which is 10. And there we go. Now instead of 10, 20, right now it's 20, 10. And there you go. That's how it works there. Now we're going to do the exact same logic for the actual matrix itself. So we're just going to do the swap operation for every single component of the matrix. And that's basically it. So yeah, let's see. So matrix swap. So we're gonna actually do the exact kind of thing that we have here. And we only need that. And so what we got here. So we got A and B matrix. Well, A and B from the matrix, right? So how we need actual pointers, not a copy of the values. So you're gonna make sure to say pointer, and probably not const. I would guess. And in fact, we could even grab that swap. Well, I've removed it apparently. Is there no swap function actually? I don't see it here, so I guess I'm just gonna do it myself then. But yeah, let's just do it here really. So basically float temporary is equal to a, and then a is equal to b, and then b is equal to temporary. Yeah. Add the constant there, and there we go. So these would basically swap those floats. Right. And yeah, that should work. That should work. So let's say matrix copy, matrix add. Let's call this matrix add, I guess. And let's just swap, let's say C with A. Basically. Well, actually here I'm talking about swapping the content itself. Though if we just wanted to swap the data, we could have just swapped the actual pointers, right? So it really depends on what you want to do here. And honestly, why would you want to swap the actual data itself? Good question. But yeah, basically this is the matrices that we have here, and data 4 by 4. So we could like say, I think inspect, or actually view as array, and then enter size 4 times 4, which is 16. And there you go, that's all the data there. Same thing with the other ones. But well, anyways, This should work. Like if we actually print both here, so matrix print A and the cd out probably here. Here we go. Matrix print A and print C. And let's print those again here. Now let's remove this for now. Now let's see what's gonna happen here. It should flip them. So we got, this is the first matrix before flipping. So identity matrix. And this is the second one. And now as you can see, they got swapped around. There we go. But yeah, I'm interested. What kind of IDE do you use? I use C-Line. C-Line, though it's actually paid, you need a license. Although if you are a student, you can get like the GitHub student pack. I'm actually a student, so I get it using this, right? So GitHub student developer pack. You could basically apply for this if you're a student. And then you would get a lot of things, like you would get GitHub Copilot, like AI, to help you with implementing this stuff. And also you would get a lot of other stuff, like free domains and all sorts of cool stuff. But yeah, which includes the JetBrains IDEs, like C-Line that I'm using here. So yeah, is there any other questions, guys? I think I'm probably gonna stop the stream at this point. There's no other questions, let me know. But yeah. Matrix swap. Cool session, man. Keep it up. Thank you, Jesus Lil. Thank you, thank you. Alright, guys. I think that should be it for today's stream. Please let me know in the comment section what you want me to cover next on C language. And if you didn't understand any concept in today's session, I honestly kind of didn't explain a lot of things. I kind of just ran over them. Honestly, in this session, I feel like I didn't explain them very well. I could have probably done a better job. But let me know if you don't really understand something in particular. Let me know in the comment section. And hopefully in a later stream, I would cover it in more depth. So yeah, that was it, guys, for the stream. And see you later. Goodbye, everyone.